blood, and if I remember correctly, we got to looking at what red blood cells are, and I think maybe I stopped at hemoglobin. Does that sound right? I mean, like I hadn't gotten to talking about hemoglobin just yet.
Oh, yeah. Red blood cells.
Oh, before I get started on things, I just wanted to ask a couple of students overnight contacted me to say that they're having trouble getting into the Concept Coach book website. Did anybody happen to try to get on that last night? Problems? Work for you? Oh, okay. If one person says they have a problem, I sometimes expect that they're having a problem. But when two people say the same thing, I figure there's something going on. When I got in this morning, I clicked on a book link, and it gave me a weird error that it like couldn't find the website or something. And so I went in a different way through my instructor concept coach thing. And it took like really long to load the site, but then it finally came up. And then since then I haven't had any problems, and I was able to text one of the students and she checked and she was able to get in too. So I think they were having a problem at some point overnight, and both of the messages I got came in after I stopped answering emails or texts. So that might have just been very late at night that they had some issue. But if you do run across something like that, please let me know as soon as you run into a problem. Because if it were like you're trying to finish up Concept Coach on time or something like that, you can't get in, then that's going to interfere with your ability to do that. But if it's a problem with the website itself, then that's beyond your control, beyond my control, and I need to know about it. If you come to me a week later and say, "Oh, I was trying to get the Concept Coach stuff done on time, and I couldn't get on the website," something like that. If I go look a week later and it works fine, then I don't know that there was a problem at the time, and I can't adjust scoring accordingly. If you run into a problem, let me know as soon as possible, and especially when several people are having the same problem, I'll know that there's something serious going on, and I can hopefully respond to it. I might not be able to fix the problem, but I at least can take into account that people are having trouble getting into the website. So if you have problems, let me know when they come up. Yes.
Well, I'm looking at my notes, and the last thing we talked about was aging, accumulation of oxidative stress.
Right.
And then I see red blood cells equals oxygen plus hemoglobin plus cytoskeleton proteins.
Mm-hmm.
Is that cytoskeleton proteins, does that include transferrin?
No. Transferrin's a protein that transfers iron. It's not part of the cytoskeleton. And it's a liver protein, basically. When red blood cells are broken down, transferrin transfers iron back to the red bone marrow to be broken down. It's not something that's found in red blood cells. So, okay, so the hemoglobin molecule, I think I actually briefly just sort of said, this is hemoglobin molecule and moved on. But that might have been because I was trying to finish saying a couple of things before the end of the class. So hemoglobin's made up of 4 subunits, which are called globins. And there are multiple globin genes in the genome. There's an alpha globin gene and a beta globin gene. And there's also a gamma globin gene, which is not represented here, and I'll explain why in a second. So 2 copies of the alpha globin gene are transcribed and translated into those subunits, and then 2 copies of the beta globin gene are transcribed and translated into those subunits. And then those 4 subunits come together to make up the hemoglobin molecule. Each subunit has in it a heme molecule, which is represented by the disc here in the first part of the drawing. And then the line drawing off to the side here is the chemical structure of heme. When you see something like this on material that we're going through, I don't mean for you to memorize a structure of what a heme unit is or something like that, or other molecules. It's more really the only way to represent graphically, visually what something is that we're talking about. So it's just a picture of that. But I won't get into the chemical structure of things too much. The one thing you do need to know, and I will point out things you do need to know about chemical structure, is just in the middle of the heme unit is an iron ion. Iron's abbreviation is Fe, which is from the Latin ferrous, as in the Ferris wheel, which is made out of iron plus steel. That iron ion has a positive 2 charge to it. The chemistry of iron is a little bit complex compared to the simpler elements that we deal with in biochemistry, oxygen, carbon, those kinds of things. So I'm not going to go into it in a lot of detail, but in that form, that positive 2 charged ion, iron will react with molecular oxygen, O2. And that's how the oxygen's held in the hemoglobin molecule. Each hemoglobin molecule has 4 heme subunits, each one with their own iron, and that will hold a bunch of oxygen. The chemistry of iron oxide is the same when we're talking about this happening in the hemoglobin in the blood, or if it's happening in just everyday situations where rust forms. Okay, rust is the exact same thing as the oxidated iron ion that we see here in the heme unit. And the color that we see in both situations is essentially the same. The red color of blood, the reddish color of rust. And they're both due to the oxidation of iron. When iron is not oxidized, when it's reacting with something else, it has a different color. We tend to think of the color of blood when it's not oxygenated as blue, which isn't exactly correct. It's more of a really dark red verging on purple, which is essentially looking kind of blue. The blue color comes from seeing veins through your skin, which are going to be that kind of purplish color because of the deoxygenated hemoglobin. And it's just simple to say, red blood versus blue blood. So that's a convention of calling it red and blue blood. But really it's just variations on the pigment properties of iron oxide within heme. So I mentioned that there's actually a third version of a globin gene besides alpha and beta. There's also a gamma globin gene. Yeah, sorry, that sounded kind of strange. But the gamma subunit is not found in hemoglobin in adults, but rather is found in fetal hemoglobin. The effects of oxygen binding to the heme unit is based on its interaction with the globin subunit. And so fetal hemoglobin holds oxygen slightly differently than adult hemoglobin. And when I say adult hemoglobin, I just mean anything from birth on. We'll look at the dynamics of oxygen binding to hemoglobin with the respiratory system later in the semester, but that is the case. And in that chapter, there's a graph showing fetal hemoglobin and adult hemoglobin differences. So we'll come back to that idea when we're talking about oxygen in the respiratory system. But those are the 4 subunits. I'll come back to life cycle in a second. Oh, I did talk about, I remember having this picture up on the screen. Was that what you guys talked about?
No.
Oh, okay. Well then, it runs together when I do multiple AMP2s in the same day. So in my other Thursday class, I talked about this. But since I'm talking about hemoglobin, let me just address this. It's a little bit further down in the chapter, but it's relevant to hemoglobin. This micrograph shows us what a sickle cell anemia red blood cells look like. It's called sickle cell because they take on that sickle-like shape to them. The reason they do that is because hemoglobin is mutated. So there's a variant of the hemoglobin beta globin gene that carries a mutation, and that's what is passed on, causing sickle cell. You have to get 2 copies of that mutated beta globin gene to have sickle cell anemia. And because of that, the beta globin subunit, or 2 of the 4 things in the figure I just showed you, is mutated and the protein doesn't fold correctly. So the hemoglobin doesn't assemble correctly, which is what results in the anemia, the lack in oxygen carrying capacity in the blood. The sickle cell comes from the fact that the unusual shape of the beta globin gene changes the shape of the red blood cell. The pointy ends of the sickle cell shape can actually be physically harmful to smaller blood vessels. If you inherit one normal beta globin gene from one parent and a mutated one from the other parent, then you do not have sickle cell anemia, but however, you're a carrier for it, you can pass that on. It would seem that a genetic disorder that can be so debilitating to such an important type of cell in the body would be probably, what's the word I'm trying to say? It would probably work its way out of the gene pool, just because people that get the disease aren't likely to pass it on because they're not going to survive to childbearing age, probably. However, the disease remains in the gene pool because having one copy of the sickle cell gene and one normal copy is actually better under circumstances than having 2 normal versions. Having 2 mutated versions is definitely not a good thing, but carrying 1 mutated version and 1 regular version of the gene actually protects people from malaria. We call that a heterozygote, which means that they carry 1 copy, or 2 different copies of the gene, the 1 normal and 1 mutated version. We also refer to it as somebody having the sickle cell trait, which is really just the added protection against malaria. Now, in locations where malaria is not prevalent, that's not an issue, but in more equatorial regions where malaria is present, carrying 1 mutated copy of the gene can actually be advantageous, and people are more likely to survive and pass those genes on. So the heterozygote state is favorable, and so the gene persists in the gene pool. It's just 25% of the time, 2 people that are carrying the disease are likely to have a child that has a full-blown disease. It has its downfall, but 50% of the time, they're likely to have children that are protected against malaria. So the gene actually persists mostly in the heterozygote state. There are other similar genetic disorders that protect against malaria also, but sickle cell is sort of the best known, best described of them. Okay. So the other thing to talk about here is a life cycle of erythrocytes or red blood cells. Did I say how long red blood cells last?
20 days.
Yeah, so that was in one of the tables that we saw earlier. And that was the oxidative stress I was talking about. They're exposed to oxygen, and oxygen is actually a dangerous chemical. It's likely to oxidize other chemicals, which can cause problems. And so red blood cells that are sort of on the front line of dealing with oxygen and are most likely to accumulate oxidative stress have a limited lifespan. And this figure here sort of runs through what goes on in the life cycle of a red blood cell. Actually, let me use the screen up here to see what I'm pointing at. So red blood cells are made through hemopoiesis. When we're talking about red blood cells, we can specifically call that erythropoiesis, which means making red blood cells as opposed to just making blood cells. In this picture, by the way, they highlight the red bone marrow in the head of the femur and the iliac crest of the pelvic bone and at the head of the humerus. In adults, those areas are where there's active red bone marrow. Most other red bone marrow has become inactive and probably become yellow bone marrow. But those are the places where you usually see them. Did I talk about bone marrow biopsies? Okay. I can never remember when semester to semester I mentioned that, but in medical dramas, they'll often have some storylines that deal with somebody that needs a bone marrow biopsy, and so they have to sample bone marrow from potential donors and see who's a viable donor. And presumably somebody in the immediate family is likely to be a viable donor because they might share the same genetics as far as blood typing and tissues and all that's concerned. And so to really heighten the medical drama, there will be usually a scene where a young child has to be tested for bone marrow biopsy. In-house, which is one of the medical dramas I've watched most often, for some reason, there's one character that's always stuck doing the bone marrow biopsies. He's a trained neurologist. Why he's a bone marrow biopsy character, I don't know, but that's what they've always done. And so they always show him sticking a needle into the hip because they're trying to get in and sample this bone marrow here. Or I suppose under certain circumstances, they could be going for the head of the femur too, which is near the hip also. And the idea is to just stick a really big needle in through the bone. Now, bone is hard tissue, so that's not the most pleasant experience. Also, bone has in it lots of nervous tissue. If you break a bone, it hurts like hell because of all the nerves. And so if you shove a big needle through bone, it's going to hurt too. And they usually play that for drama on the show. But I like this picture. It does depict sort of where the major regions of functional red bone marrow is. We looked at the flow chart before about how the multipotent stem cell becomes various types of blood cells. And so in the red bone marrow, that stem cell will go through a few changes to become the red blood cell. The reticulocyte will eject its nucleus and the red blood cell will move into circulation. After about 120 days, the red blood cells will be broken down. This thing looks like a paint splatter is a white blood cell. We'll talk about those in a lot more detail in the immune system. But one thing they do is they break down cellular debris and other types of cells in circulation or in bodily fluids. And so this cell is basically ingesting a red blood cell and breaking it down to its component parts. All of the component parts are basically recycled. The proteins are broken down to amino acids to be used to make new proteins in the future. The The other proteins in the cell are broken down likewise. The cell membrane will be broken down, and those phospholipids will be recycled and they can be reused. The heme molecule is taken out. It's not broken down. Instead, the heme group part, it goes off to the side, and I'll talk about what that does in a second. And then the iron ions are removed from that, and it's bound up in this molecule transferrin, which Ali asked about earlier. The word transferrin sounds like it's referring to something that transfers, which it does. But actually, if you consider the breakdown of the word, the fer part in transfer has two R's to it, which is actually pointing out that it's referring to iron in the sense of ferrous, like I mentioned before. So it transfers iron, and it moves that iron ion from wherever it's broken down back to the red bone marrow to be recycled into new hemoglobin. Now, I said wherever it happens to be broken down. They show here just a white blood cell in the bloodstream. That's most likely going to be in bone marrow, which means the transferrin doesn't have to far to go, or in the liver, which is where transferrin is actually made, and also in the spleen, which is basically, along with the liver, a big filter for blood. So any of those places are where the red blood cells are usually broken down and recycled, and the iron is carried by transferrin back to the red bone marrow to be reused in new hemoglobin.
Could you repeat where it's typically broken down at again?
It says right here in the caption of this part, which is the bone marrow itself, or liver, or the spleen. Now the heme group, let me just go back. The thing that I point out drawn here, aside from the iron ion that's been removed from it, the rest of the heme group then gets transferred to the liver. Might have already been in the liver if that's where the red blood cells broken down. But in the liver, it's enzymatically changed into a different molecule called biliverdin, which is then changed into bilirubin. Now, in those two words, biliverdin and bilirubin, the bili part comes from the word bile, because liver makes a digestive juice called bile. And what the heme group becomes is a bile salt, a component of bile that helps bile do its job. The two names here just referring to just chemical differences in the molecule. The root in biliverdin comes from the same place that we get the word verdant, which means lush and green, because I believe biliverdin technically is a green pigment. And then rube is the root where we get the word ruby, which is a red gem. And I believe that's supposed to be because bilirubin is a red pigment. However, when you think bile, it's usually yellow in color. You've probably seen bile if you've ever spit up a very liquidy fluid from your stomach. That's going to include some bile probably from the small intestine. The names of these molecules seem to say green and red, but I've never seen bile to have a red tint to it because of bilirubin in it. What's not included here is what the bilirubin ends up doing. So it's secreted from the liver as bile into the small intestine, which plays a role in helping break down lipids in our diet. And I'll talk about that role a lot more in the digestive system. Most of the bilirubin will be recycled and taken back up into the liver to make more bile. It doesn't physically change in doing its job within bile. However, some of it doesn't get taken back up in the bloodstream, and it stays in the intestines. And bilirubin, as it passes through the intestines, will be modified along the way into a couple of different other molecules. One of them is urobilinogen, and again, it has the bil root in it, referring to its role for bile. But it also has uro in it, which is pointing to the fact that some of the urobilinogen ends up being filtered out of the blood in the kidneys and becomes a component of urine. I think actually that's a fairly minor thing. It's like 5% of it ends up in the urine. Most of the urobilinogen actually ends up being modified again in the small intestine, or in the probably the large intestine, into a molecule called stercobilin. Again, the bil in it referring to its once being part of bile. Stercobilin's claim to fame is that's the pigment that gives poop its color. Okay? It's a tannish to brown pigment, and it gives your feces its color. The color of your feces can actually point to liver function. So if you don't have tan to brown colored poop, that might be because your liver's not making bile properly. Or it could be that your intestines aren't processing it properly. So that's not in this figure again. It's kind of showing you where the heme molecule ends up going. I can't remember if that pathway from bilirubin to stercobilin is covered in the digestive system chapter in the book here. If it is, we'll come back to that, but I don't recall offhand. But anyways, this figure is highlighting the what happens to red blood cells. They're made, and about 120 days later, they're broken down. Most everything gets recycled, except for the heme molecule that's instead repurposed to be part of bile, which is a digestive substance. Yes, that's the end of that section on red blood cells. So the other types of cells in the blood are leukocytes and platelets. I'm only going to briefly talk about leukocytes here. We're going to save most of what white blood cells are about for the immune system. And then in talking about platelets, I actually want to talk about blood clotting, which I believe is the next section of the book anyways. So white blood cells are important for immune function. There's a lot of function to cover about about white blood cells, and we'll talk about it in a lot more detail with the immune chapter coming up after we finish the cardiovascular system. But here they're talking about, or they're showing how white blood cells move from circulation, from the blood, into tissues where we have injury or infection. So here they're showing a cut through the skin, and these sort of pill-shaped things are representing bacteria that have moved in through the cut wound. Let me turn the light off for a second. I want to point something out to you. So you might not be able to quite see it on the screen here, but I want to point it out so that you're aware. There's a little squiggly line right here, okay, wavy line, whatever you want to call it, separating this part of the picture from this part of the picture. What is that line separating? What's on this side of the wavy line? What's on this side of the wavy line? And this is a question asking you to think about what you learned in English. Right, it's the dividing line between the dermis and the epidermis. Okay. Which side is which?
Is the top layer?
Okay.
Who agrees with that?
Where the cut is.
Yeah, that's what I said.
Dermis is the deep part of your skin. Epidermis, meaning on top of the dermis, is the epithelial layer. So the cut we see here is going all the way down to the dermis, okay, because the epidermis provides a barrier. If you only cut through the epidermis, then that stratified squamous epithelium provides protection and bacteria can't get in. You have to cut all the way through the epidermis to get to the dermis for bacteria to get in. Okay. So we have an infection coming in through this wound in the skin, and when that happens, white blood cells will move out of circulation and into the local tissue, the dermis, to play a role in fighting off that infection. they're pointing out these different cells. They're naming them. This is an eosinophil, this is a monocyte, and this is a neutrophil. There are two other types of white blood cells, lymphocytes, which don't do what I'm about to describe, and basophils, which are very, very rare white blood cells and wouldn't really be involved in what's going on here. And, that's actually something I'll bring up when we get to the immune system. Eosinophils are actually fairly rare white blood cells also, but they kind of fit in with these other two. Neutrophils and monocytes are very prevalent. Neutrophils make up about 2/3 of the white blood cells in your system, and monocytes make up a little less than 10% of the cells, white blood cells. When they leave circulation or leave the circulatory system and move into surrounding tissues, they become activated to be cells that gobble up, again, debris, damage, and pathogens. When a monocyte is going to move into tissue and do its job, we call it a macrophage. When a neutrophil does it, we actually technically still call it a neutrophil, but we refer to it also as a phagocytic cell. Okay. Phago means eat. It's the root of the word esophagus, and just from Greek means to eat. And then cyte is cell. So a phagocytic cell is a cell that eats other cells. A macrophage is just a really big phagocyte. Now, a macrophage isn't necessarily that much bigger than a neutrophil phagocyte. It might be the difference between like 15 micrometer and 20 micrometer diameter, but they are the bigger ones out there. And when they need to leave circulation, the only way that they can get out is in the cracks between the squamous cells that make up the blood vessel wall. And so that's what we see here. They're squeezing through. The way that they squeeze through is helped by the fact that their nuclei are very strange shapes. Instead of having just a spherical nucleus, the nucleus is usually what we would call lobed. So it's sort of broken or separated out into different regions, which are all connected together. It's still one nucleus. But it can squeeze a little bit of the nucleus through the gap in the blood vessel at a time, and then the whole thing can squeeze through. It's sort of like, I know, cats and rodents and those sorts of animals that can squeeze through very small areas. My dog would get stuck trying to get through something really small, but I believe cats are fairly known for this. They can actually sort of squeeze their body through, and I don't quite know how they do it, if they like dislocate parts of their skeleton or whatever. But white blood cells can kind of do the same thing. And they show that happening here, that here's part of the nucleus that's been pushed through, and here's part that hasn't gone through yet, and the cell's sort of squeezing through that space. Monocytes have slightly different looking nuclei, but they still can do the same thing. They can squeeze through those gaps and get to the site of infection. And then those cells, just like we saw with the 120-day-old red blood cells, will just eat things. Okay, they'll ingest the pathogens or any debris from the wound site. If there are epithelial cells that got damaged and they're breaking off, they can be cleared away by those phagocytic cells, clearing it all off. Okay.
Professor, how
Yeah.
much percent did you say the neutrophil was in your body?
Neutrophils are very common. They're like 2/3 of the cells, white blood cells in your circulatory system. We'll talk about the specific numbers when we get to the immune system, but roughly speaking, about that much. I guess actually before showing you that picture, it would make a little more sense to talk about this. Because these have pictures of the white blood cells and the funny nuclei. Leukocytes, or white blood cells, fall into two categories, what we call granular leukocytes, and then the opposite of that is agranular leukocytes, which we'll see in a second. To call them granular is referring to the fact that under the microscope, they have grainy inclusions in their cytoplasm. How obvious those inclusions are vary by the type. Neutrophils, which is the first one here, you can't read the title very well. They have grainy inclusions, but they're actually kind of hard to see. They're there, but they're hard to see. And then eosinophils and basophils have more obvious grainy inclusions. It would seem that the basophils have sort of the most obvious grainy inclusions, but I can't say that that's necessarily true. The titles or the names of those three types of cells, all of the granular leukocytes, end in phil, and it's neutrophil, eosinophil, and basophil. The roots of those words, neutro, eosino, and baso, refer to pH. Neutrophil is neutral, loving cell. Phil as in hydrophilic, that kind of word. Eosinophil is acidic loving, and basophil is basic loving, or alkali loving. That's actually just referring to what they look like when they're stained, how they react with the stain of varying pHs, I think. It doesn't mean that those cells have different pHs. It's just how they interact with the stain in a very unusual situation. In your body, they don't necessarily have grainy inclusions that you can see in the cell. To see them, you have to stain them. And how they react with the stain is what the name is referring to. But they all exist in your body at the same roughly 7.35 pH. Okay. Neutrophils are the most common of all of the white blood cells in your system. And eosinophils and basophils are least common. Basophils the absolute least, and eosinophils a close second to last in line, I guess you'd say. And then the other group are called agranular leukocytes, which I'd kind of hoped that they'd have a picture of there too, but they don't. They're called agranular leukocytes because they do not have grainy inclusions in their cytoplasm when you look at them under the microscope. And the two types there are lymphocytes and monocytes. So if you're trying to keep straight which type belongs to which classification, if the name has phil in it, it's a granular leukocyte. And if the name has cyte in it, it's an agranular leukocyte. Monocytes I just described are the things that become macrophages. And lymphocytes are involved in an important part of immunity that we'll talk about in a lot of detail when we get to that chapter. Let me type this up so it gets on. I hope this will be visible to you on the screen, but there we go. Yeah, you can do that. So white blood cells, or leukocytes, come in two groups. There are granular, oops, can't type, granular, which is neutrophil, oops, eosinophil, and basophil. It's a little bit. And agranular, which are lymphocytes and monocytes. So just in the name, you can tell which is which. Ends with phil, it's granular. Ends with cyte, it's agranular. Also, you can remember which is most prevalent down to which is least prevalent with the mnemonic, never let monkeys eat bananas. Okay. The first letter of each of those words corresponds to the first letter of one of the cells above. And that order is the order of prevalence of those cells. So neutrophils are about 2/3 of the cells. Well, let me put this all in about 65% of the cells. Lymphocytes are, I believe, 20 to 25%. Monocytes are less than 10% of the cells. Eosinophils are about, I think, 2 to 3% of the white blood cells, and basophils are around 1%. So just that list there, never let monkeys eat bananas, helps you remember the names of the cells and the order in which they're most prevalent. Now, the numbers I've put in there aren't necessarily going to add up to 100 perfectly, because some of them are approximations and some of them are ranges, but it will all work out to about 100% overall. And neutrophils are just the most common, basophils the least common. So anything else about white blood cells that we're going to cover in this course will be covered in the immune system, and we'll talk about them in a lot of detail. What their functions are, how they mature into functional cells, what they do, et cetera, et cetera. So we'll get back to that. Then we have platelets, which are also known as thrombocytes because they are blood clotting cells. Thrombus means blood clot, so thrombocyte means the clotting cell. We just normally call them platelets, but thrombocyte goes with lymphocyte and erythrocyte as far as the Greek names for those cells. Platelets are actually cell fragments of a larger cell called a megakaryocyte. I think I introduced that term when I was talking about the stem cell flow chart, but there they are then. They end up being very, very small little fragments of that megakaryocyte. Here they say 2 to 4 microns in diameter. I've seen elsewhere saying 1 to 2 microns in diameter. To say in diameter for a platelet is actually kind of weird because they're not very spherical. Being cell fragments, they're very amorphous in shape. And so depending on what source you go to and how you measure their diameter, you're probably going to get different ranges. So just they're in the 1 to 4 micron range in size. But one megakaryocyte breaks down into a couple or few thousand fragments that are all platelets. Okay. The next section is dealing with hemostasis, which is the formal word for blood clotting. Now, notice that that's not homeostasis, it's hemostasis. The hemo part of the word is the root that means blood, okay, like hemoglobin. And then stasis means stay or stable or whatever you want to say. So blood clotting is keeping the blood in place, not letting it leave circulation. That's what it's about. Blood clotting has 3 major components to it, 3 major events. There's the vascular spasm, the formation of the platelet plug, and coagulation. A spasm is a rapid involuntary contraction of a muscle. And so vascular spasm is just talking about when a blood vessel is damaged, which is going to cause bleeding, the vascular wall, the blood vessel wall, will constrict as the smooth muscle in it contracts. That will limit the amount of blood that can flow through that particular blood vessel, and therefore limit the amount of blood that's going to be lost at the site of damage. In the next chapter about blood vessels, we'll talk about blood flow in a little bit more detail, but basically, blood flows down the path of least resistance. So if you constrict a blood vessel that's going to be narrower and it's going to be harder for blood to flow through it. And so blood is going to tend to go elsewhere where the vessels are wider and blood flows easier. So that limits the amount of blood loss. Also, it brings the damaged tissue potentially closer together so that it can heal faster. That happens immediately. So we sort of think of it as the first step because it's started and finished before anything else takes place. Then the next step is formation of a platelet plug, and this is what platelets are about. They form a temporary clot, plugging up wherever the blood loss is taking place. But it's not a permanent clot, okay, just temporary. Then the third step is coagulation, which means blood clotting, which might seem kind of silly for the third word to kind of mean the same thing as the whole process. But coagulation is referring to specifically the formation of the more permanent blood clot. Now, using the word permanent is a little strange here. You don't permanently clot something. The clot stays in place until the tissue heals. But it's more persistent than a platelet plug. A platelet plug is just an immediate stoppage so that the clot can form. The clot is essentially a mesh of fibrous proteins that seals off the hole in the circulatory system and will actually physically pull the damaged edges of the blood vessel closer together so that it can heal up quicker. Platelet plugs will help out with that, but they're not as persistent. They get replaced by that fibrous clot.
Well, that pulling happens at the first step.
Well, you can kind of say that all of these steps have something to do with helping the wound close up. The spasm might bring the cut edges closer together, but not always. The platelets will actually help with that, and then the fibrous clot will also do it. Everything kind of tries to pull the cut or damaged tissue closer together so that it can heal faster. So the book has this figure that explains what's going on in clotting. And I want to break it down for you because I don't think the picture presents the information in the most straightforward way. For one, the picture has two processes seemingly side by side, as if what's drawn in the pictures on this side and the series of events described on this side coincide. Like, this is what it looks like, and this is how we describe it. That is not how it's done. This is a protein cascade, and I'll talk about that a little bit later. So it doesn't quite correspond to what's going on over here, which is essentially those three things I just mentioned: the vascular spasm, the platelet plug, and coagulation. Platelet plug and coagulation are actually kind of taking place at the same time. The platelet plug is sort of a faster way to stop blood loss, and the coagulation takes longer, but then becomes more permanent, so to speak, or more persistent. And we can kind of say, since this is the end point of what's happening, it corresponds with what's happening down here, but it's not a perfect correlation between these two sides of the picture. So let me zoom in on some of this so we can see it better. Up at the top here, we have a depiction of what a vascular spasm is. So the first picture here isn't the what happens for healing. This is a depiction of what the injury would be. So not necessarily the case here, but imagine the picture we saw earlier with the cut through the epidermis down to the dermis level. If you do that, then blood vessels that are right underneath the epidermis could entirely be damaged like we see here. But all over the body, this kind of thing can happen. It doesn't necessarily have to be a complete rupture all the way through the blood vessel. There could just be a hole on one side, not necessarily on both, but that's the way that it's here. when there's damage to the blood vessel like this, the first thing that happens is a vascular spasm, which is the smooth muscle around the circumference of the blood vessel will constrict, and that'll narrow the blood vessel. That will limit the amount of blood that can move through that particular vessel. Blood will tend to go to other vessels to get to flow more easily. It allows for some healing to take place there. Now, the way that this is depicted, what I was saying about the spasm potentially bringing cut ends closer together doesn't really apply. That's because they have a complete severed vessel here. But possibly if it was just a cut on one side, constriction of the muscle here might shorten the length a little bit and bring the cut edges closer together. Not if it's a complete sever through, but if there's just a hole on one side, it's possible that the spasm can help with that. That's not the most important part of what the spasm does. Spasm is just narrowing the blood vessel to limit blood flow through the area. Then the next thing is a platelet plug formation. And what happens here is platelets, which are depicted here, these are the cell fragments I was talking about, they become activated, which in this drawing is the different shape that we see, that a normal platelet gets activated as depicted by this blue or purple arrow, whatever it is. So this is what they look like when they're activated, according to this drawing. When they're activated, they will stick together and they'll block off where the damage is. They'll also stick to the edges of the blood vessel, and they can pull it closer together to allow the tissue to heal or whatever. Again, that aspect of what clotting does to bring cut edges closer together doesn't entirely make sense in this complete section of the blood vessel. But it could potentially close off the blood vessel, and it'll eventually just be a dead end somewhere in circulation. It does limit the amount of blood loss. Now, platelets getting activated is a positive feedback cycle. Okay? It's one of the few positive feedback cycles we see in physiology. When a platelet is activated, it releases a chemical that will activate platelets. And when those new platelets are activated, they release a chemical that will activate platelets. And so activated platelets activate new platelets, which activate new platelets, which activate new platelets, which activate platelets. And more platelets are going to move into this area and become part of that plug, stopping the blood loss and beginning the process of healing. To call something a positive feedback cycle implies that something else is going to shut it down. Okay? What that something else isn't necessarily explicitly stated. In this case, it's when blood loss ends, then the blood clotting reactions will all stop, and the platelets will stop being activated. But the platelets themselves just tell other platelets to become activated, and then they tell other platelets, and then they tell other platelets. And it can potentially run out of control. You just keep activating platelets, they're just going to start to form a plug and interfere with things. In fact, there are various situations where people can mistakenly throw a clot, which is usually because platelets get activated by accident. What initially activates platelets, there are several things that can do it. They're generally going to fall into two major groups, what we call extrinsic factors and what we call intrinsic factors. Extrinsic means from outside. Intrinsic means from inside. And in this context, that's referring to inside or outside of the blood. Extrinsic factors that cause platelet activation are usually signs of damage of the blood vessel. Okay, so if something ruptures the blood vessel, then tissue that's normally not adjacent to the blood will become exposed to the blood and activate those platelets. The main thing that does that is collagen. So the inner surface of the blood vessel is a solid epithelium. Beyond that epithelium, there's going to be connective tissue or something like that that has collagen in it. If you cut through the epithelium, if you rupture the epithelium, the collagen outside will then interact with the blood, and collagen will activate platelets. Also, blood vessel walls, well, I should say any tissue, not just blood vessel walls, but here we're talking about damage to a blood vessel wall. Any tissue releases chemicals that and called tissue factors that just indicate that damage has happened to the tissue. And so as the cells in this wall here are broken as they're damaged, they'll release signals called tissue factor, which can then lead to activation of the platelets. Those are extrinsic factors, things from outside the blood. Intrinsic factors that start this are things that are within the blood, which is basically talking about the platelets. So these yellow dots here represent chemicals that activated platelets release to activate other platelets. And they end up, that's the intrinsic signal. What causes a platelet to initially start releasing those factors are usually extrinsic signals, like collagen or tissue factor, something like that. But there are situations where platelets can accidentally become activated, usually when two platelets run into each other. This picture is not a good representation of the idea, but I'm going to work with it because of what it does show. The best representation of this idea is in a Plavix commercial. Okay. You heard of Plavix? Anybody? Anybody watch television? Pay attention to commercials? Plavix is an anticoagulant drug for people that are at risk for strokes and that sort of thing. They'll take Plavix. Plavix interferes with platelets being activated, which, if you're at risk for stroke, is a good thing to stop from happening. It does mean that you're at higher risk for spontaneous bleeding or something like that. Well, I shouldn't say spontaneous bleeding, but uncontrolled bleeding. If you damage tissue, then this process will be a little bit harder. But in the Plavix commercial, what they usually depict is a blood vessel that's narrowing because one wall is building up a cholesterol plaque. So cholesterol, if somebody has high cholesterol, will work its way into the wall of the blood vessel, building up and narrowing that blood vessel. Okay, so in this picture, we see a normal wide blood vessel here that's narrowing because of the vascular spasm. But imagine that these thickening walls here are actually because of cholesterol. As these platelets are flying through, when they get to the narrower part, they're going to sort of be squeezed together, as with everything else. When platelets start to run into each other, they start activating each other, even if there's no extrinsic factor. That's intrinsic. So platelets will activate themselves. The point of taking a drug like Plavix to reduce the chance of stroke is actually to keep platelets from activating each other. It can also interfere with the blood clotting process, but it's better to know that you're going to have problems with blood clotting and not get strokes rather than have normal blood clotting and a higher incidence of strokes. So you take a drug for that reason. So those are extrinsic and intrinsic factors that will cause platelet activation. And then the final step is coagulation, which is formation of the fibrous mesh that is the blood clot. Now, the protein that's fibrous in the clot is called fibrin. Not a very inventive name. It really just means fibrous protein. And in the scanning electron micrograph down below, we see representations of fibrous proteins that are all kind of making a mesh together. And red blood cells are being trapped in there, as are platelets. There are not any platelets pointed out or obvious in this, but maybe that's a little cell fragment platelet. They get caught in that mesh. So all of that becomes the blood clot. The blood clot doesn't have to be on the surface of your skin. You're only going to see a blood clot on the surface of your skin if you cut through your skin. But when you get a blood clot on the surface of your skin, that's what we call a scab. Okay? Scabs are usually kind of reddish in color because red blood cells get caught in that fibrin mesh. Technically, the same thing is going on inside when there's some sort of damage to the blood vessel internally, forming a blood clot. We just don't call it a scab when it's internal. It's just a blood clot. But that's coagulation, the protein mesh forming there. So again, on that side, we basically see the three major parts: vascular spasm, the platelet blood formation, and coagulation. On this side of the figure, they're illustrating the process of what's called the clotting factors. Clotting factors are proteins found in the plasma. Most of them, actually probably all of them, are made by the liver. And they are the chemical process, not all of them are made in the liver, I should take that back, but most of them are made in the liver. And they circulate through the blood for the most part so that they're available when they're needed to do this. However, clotting is something that has to be very tightly regulated. You don't want clots to form spontaneously, you only want them to form when they're needed. And so there's a whole bunch of clotting factors involved. They're referred to usually by a number. So clotting factor 1, clotting factor 2, et cetera, et cetera. The numbers are represented in Roman numerals, and so in this picture, what they're showing us are just circles or starburst patterns with those numbers in them. I don't need you to know the numbers here necessarily, just to understand the idea of this process. So here's a clotting factor here. It happens to be clotting factor 12. Something happens and causes it to be activated. So now it's 12A, the A for activated, and in the picture it's a starburst. And once it's activated, it then causes the activation of another factor. And when that's activated, it causes the activation of another factor. And that interacts with another factor, which then causes the activation of another factor, which interacts with another factor, which causes these reactions to take place. Okay. So there's several different things that have to happen. Okay. It gets started at one end, but each of these reactions have to take place for blood clotting to progress. We can regulate blood clotting by potentially interfering with anything along the pathway. If a blood clot starts to form and it's not supposed to, then if we can't stop it at the beginning, we can stop it further along the process and you don't form a blood clot. Okay? We can regulate the process. There are two sides to how this can start, which I actually kind of already set up for you. And they end up converging onto one thing that gives rise to what we call the final common pathway. The two pathways that lead into that are called the intrinsic pathway and the extrinsic pathway. Now, the book has made a serious error here. The way that they've defined intrinsic and extrinsic is not appropriate. It's not what it really means. But I just define those two words for you. So the intrinsic pathway is anything that leads to clotting because of something that's happening within the blood itself, that starts with the blood. That would basically be platelets activating each other. And then the extrinsic pathway is anything that starts clotting that happens outside of the blood. The problem with what the book says is they're not talking about intrinsic and extrinsic to the blood, which is what it should be, but rather intrinsic and extrinsic to the blood vessels, which is not what those terms are supposed to mean in clotting. So when they say intrinsic pathway, they say damaged vessel wall. And then extrinsic, they say trauma to extravascular cells, which is just not correct. Extrinsic is damage to the vessel wall, damage to cells that are not in the blood. The circle here, which is labeled tissue clotting factor 3, this is actually tissue factor that I mentioned earlier, which damaged cells release. If you damage your skin, cut through the epidermis, cut into the dermis, and therefore break some blood vessels in the process, tissue factor is going to be released from all of the tissues that are damaged there. The epidermis, the dermis, the blood vessels, et cetera, et cetera. Everything's going to be releasing tissue factor. which will lead to the extrinsic pathway for forming blood clots. But once something causes platelets to be activated, which might be the collagen that the blood's now exposed to or something like that, once it gets started, that's the intrinsic pathway. When you really are losing blood, the intrinsic pathway is really kind of hard to tell from the extrinsic pathway because it's started by something outside the blood. But the intrinsic pathway is describing things that can happen accidentally inside the blood, like when cholesterol blood builds up on your blood vessel walls, and it narrows the blood vessels, and so platelets start running into each other and activating each other. That'll lead to blood clots, which will lead to strokes and that sort of thing, which you don't want. So there are these two pathways that play a role. They eventually converge down here. There's clotting factor 10, this is its activated form, and there's clotting factor 5, its activated form here. I can't remember which of these it is, but one of them, or maybe both of them together, are referred to as an enzyme prothrombinase. The ASE ending of that tells you that it's an enzyme, and the rest of the word tells you what it does. What prothrombinase does is it converts prothrombin into thrombin. Prothrombin is a proenzyme. Okay? It's not an enzyme, it's going to become an enzyme. And then thrombin is the enzyme that it becomes. Thrombin as an enzyme will then break down fibrinogen to cause it to become fibrin. Fibrin, I told you a little while ago, is the protein that's the fibrous mesh of the blood clot. Now, let me talk a little bit about proenzymes. Okay. Prothrombin, let's say it's shaped like this. And this part right here is the active site of the enzyme. Let me hold a little bit better. Let's say this is the active site of the enzyme. This binds to fibrinogen and converts it to fibrin. But right now, this little piece here is blocking the active site. So it's not an active enzyme. What prothrombinase does is it comes along and cuts this piece off. Now, I'm not going to actually cut my little toy here because I don't want to damage it. But where I've put my fingers here like a pair of scissors, that's what the prothrombinase enzyme is doing. Cutting that off, so now the active site of thrombin is exposed, and thrombin can do its job. Okay. Fibrinogen, when it's broken down, something similar happens. Fibrinogen is actually one of the major plasma proteins that we learned about last time. It's a soluble protein. It floats around in the plasma. What thrombin does is it breaks fibrinogen down into a smaller component, which is no longer soluble, and we call that fibrin. So again, let's say this is fibrinogen is floating around, and by breaking this part off, this thing then becomes the fibrin molecule that is the clotting protein. Kind of hard to do a great job of suggesting what's happening with that with these little foldy things, but that's the idea. It's about shape. A proenzyme like prothrombin just has a little bit that interferes with the enzymatic activity, and when you remove that little bit, you get the enzyme, thrombin. Thrombin's job is to convert fibrinogen into fibrin, which is not a proenzyme enzyme, it's just a soluble protein to an insoluble protein. But that's what it does. Now, what's not represented here is that there's more positive feedback in this clotting process, and that's at thrombin. Thrombin's main purpose is to convert fibrinogen into fibrin and cause the coagulation, the clot formation itself. But it can also feed back. Part of the feedback is going to go to prothrombinase, and part of the feedback is going to go, actually for this picture, it should go this way, to somewhere in the intrinsic pathway and activate more platelets. If it goes directly back to prothrombinase, thrombin makes more prothrombinase, which converts more prothrombin into thrombin, which can make blood clots, and then that more thrombin can
come back here, make more prothrombinase, that converts more prothrombin into thrombin to make a more clot. And thrombin will feed back to make more prothrombinase, which will convert prothrombin into thrombin and make more of a clot. Thrombin will feed back to more prothrombinase, convert more prothrombin into thrombin, et cetera, et cetera. That's positive feedback. Okay. I've practiced saying that enough times, but imagine I did that again, saying it 4 or 5 times, and thrombin feeds back to activate more platelets, which causes more prothrombinase to be made, which converts more prothrombin into thrombin, more clots made. Okay. So it actually can feed back into 2 different places. And that's more positive feedback that we see in clotting. What's the point of positive feedback? If it's something that can run out of control, why do we even have it at all? What? Yeah, you could say that, but that doesn't really get to the heart of the question. Why do you want to control clotting that way?
So you don't bleed out and die. If it doesn't clot, you don't bleed out.
Well, yes, if it doesn't clot, you'll bleed out, but the positive feedback speeds the clotting process up. Okay? So if I told you to go close every door in this building so that people can't get out, it'd take you a long time to close all those doors. But if I told you to tell more people and everybody go close the doors, then each person you tell can close more doors in the building and less people can get out. And so that positive feedback, you telling somebody else to tell somebody else to tell somebody else, everybody goes and closes doors, it just speeds up the process. Okay? So activating more platelets or making more prothrombinase just speeds up the process. Within positive feedback in physiology, there's nothing built into the process that ends the cycle. Okay? If platelets are getting activated, they're going to continue to activate each other as long as they can. Okay? Something outside of the system has to shut it down. Okay? And that's the end of the blood loss. Okay? But you want to speed up the end of the blood loss by having that positive feedback in the system. So, that's our little trip through clotting. Here's sort of a depiction of what's going on here. On this side, don't worry about the numbers. I've talked about the specific ones you need to know by name. Tissue factor, prothrombinase, prothrombin, thrombin, fibrinogen. Those are the names you need to know. Anything else that's just a number, you don't need to know that specifically. Just know that there's a bunch of stuff going on there. And the intrinsic versus extrinsic stuff. Hold on just a second. This will just take me a minute. So that's the blood clotting stuff. The next section is blood typing, which I covered in lab. And then we move on from there to start the heart material, which is what we'll start on Thursday. As far as due dates are concerned, I better double check, but I'm pretty sure I set the due date for the the blood chapter assignments for midnight tomorrow, before you come into class tomorrow, Thursday. The concept coach stuff for the heart chapter would also be due before you come into class on Thursday. I don't remember if I said this before, but within the concept coach system, it only tells me what day you complete material on. So you need to complete it by midnight the day before. So if we're doing material on Thursday the 24th, let's say Thursday the 24th, then I need to see in concept coach that you completed it by the 23rd. Okay, so by midnight on the 23rd, and it'll be counted done on time. Okay, and that's the way it'll go on forward, because it doesn't give me a specific time. If you could tell me that you did it by 11 a.m. on the 24th, then I can give you credit for doing it on time. But it only tells me what calendar day you do it, so you have to do it by midnight the day before, which is the due date for everything else. So that's all for today. I'll see half of you in class in lab tomorrow, and the rest of you in lecture on Thursday.